Ancient Greek mathematicians used but did not formalize a method of approximating areas of irregularly shaped objects by using finite sums of regularly shaped objects. Hi, my name is Tom Atwater, and today's lesson is learning to use the rectangular approximation method to estimate areas. We refer to that as the RAM method, RAM. Let's start with an example. What we have is finding the distance traveled when the velocity varies. A particle starts at x equals 0 and moves along the x-axis with a velocity v of t equals t squared for time t greater than or equal to 0. Where is the particle at time t equals 3? What I want to show you, though, is to make sure it's clear how the velocity and the total distance are related. So let me draw a quick diagram for you where the y-axis is the rate. So I'm going to stick with miles per hour. And the x-axis is time, which, of course, we'll measure in hours. Now, let's say you're traveling in a car at 60 miles per hour. And it's a constant 60 miles per hour. And now let's say that you did that for 5 hours. If I said to you, how far have you traveled? You'd say, well, that's simple. You just multiply 5 times 60, and you've traveled 300 miles. Well, that's interesting because now let's look at this, because that really is multiplying. And of course, this is not to scale. Sorry, that 5 I didn't mean to put there. This is 5 here for the number of hours. 60 is the miles per hour. And we really are finding the area of the rectangle. And again, that's not drawn to scale because obviously this is much shorter and it should be longer than that. So what we're saying is that when we want to find the area, the total distance traveled, that it turns out to be the area underneath the velocity curve. Now, this particular velocity was a constant velocity. I wanted to show you that because what we're going to move on to now is when the velocity changes. And so, let me take the example that we're working with right now. Here we show that the particle is moving along the x-axis, and there's our time measured in the 3 seconds that we talked about. The velocity is measured as v equals t squared. And that's what this blue line is. That's the velocity curve right here. And what I've done is I've said, okay, let's divide this up into small rectangles. And in particular, these, of course, look very smooth because they're in line with the velocity curve. But if we look at them more closely, that is, we zoom in on them, what we'll notice is that we can create rectangles like I've done here, the blow-up of which is here. And let's talk about that, because what we're saying is we have a height which is going to be the midpoint of the width of this rectangle. And the width of the rectangle is something that we decide by dividing up the total length into a certain number of subintervals. And in this particular case, when we did it, we can see that I did it into 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 subintervals. And so what we do is this. We say, okay, each of these little rectangles is equal to the height times the width. And for this particular one, each of the widths is equal to 0.25. That is 1/4. So that's my width. Now my height, how do we figure that out? We go back to our v equals t squared, and we plug into that whatever the midpoint of each interval is. And that's what I have in this table right here. Although those numbers may be too small for you to see, let me read one of them to you. For the first subinterval from 0 to 1/4, the midpoint of that would be 1/8. So we take the 1/8 and we plug it into t squared, and of course we get 1/64. And then we multiply the midpoint times the height, and we get 1/256 as the area of the first rectangle. I'm not going to take you through every rectangle, but you can see down here that each of the areas of the rectangle are written down, and there's 10 of them, and this number here is the approximation, and that number is 8.98. So that number approximates the total distance traveled by that particle moving along the x-axis with a velocity of t squared. Okay, great. Now, let's take a look at using the RAM method for another problem. Use RAM to estimate the area of the region enclosed between the graph of f and the x-axis for the interval inclusive a to b inclusive. And the function we have is f of x equals x squared minus x plus 3. And again, you have a equals 0 and b equals 3. So this time, let's look at the picture that I have off of a graphing calculator. And let me make sure it's clear to you that these lines that I've drawn here, because I've divided it up into subintervals, those did not come off the calculator. Simply this curve here that I'm outlining in blue is what came off the calculator. All right, having told you that, these lines are the ones that I've drawn in to create my rectangles. But again, on a blow up, if I were to blow this up for you, we would take, for example, and create a rectangle like this and look at the height as described by the midpoint, right? And then our width of each rectangle. Well, once again, we know this went from, let me use a different color. It went from 0 up to 3. I've divided it into 12 equal sections, so, or subintervals. So each rectangle is 0.25 wide. And then we can calculate the height of each rectangle by using the original f of x and plugging in the midpoint of each of these rectangles. And so, again, I'm not going to take you through each one of the rectangles, but the basic idea would be that we would multiply to get this approximation. We would have the 0.25, which is the width of each little rectangle, and then we would multiply that times f of the midpoints. And the first midpoint would be 0.125. The second midpoint would be 0.375. And then they would continue to increase and go all through all 12 of them. And eventually, when you do this, you would come out with 13.5 as the approximation for that particular area under the curve. Okay, so now let's take a look at another type of an example, because we can also use RAM to estimate volumes. And so we're going to use RAM to estimate the volume of a sphere. So let's take a look at this. estimate the volume of a sphere that has a radius of 4. So I've drawn some, or I've actually taken some pictures from the textbook so that I can show you how we go about this process. First of all, you should recognize this function, which is y equals the square root of 16 minus x squared, as being the top half of a circle. That's outlined in blue, and what we're saying is we're going to take that top half of the circle and we're going to rotate it or spin it around the x-axis, which will then form the sphere. So that's what we're going to say to start. All right, let's move to the second picture. Then what's going to happen is we're going to slice up the sphere into these little mini cylinders. And each, just like we divided up the curve into those rectangles, into subintervals, that's what we're doing here, except that instead of making a rectangle, we're actually making what is a very, very thin cylinder. And let's move to the third picture, where we can see that using the y equals square root of 16 minus x squared, and we take a midpoint of one of the slices, and we plug it into our formula, and it would be that the height here would be equal to the square root of 16 minus the midpoint squared. So that gives us our height, and of course, the width always depends on how many subintervals we divide it into. So let me write down, however, what we're looking at in terms of the volume. The volume of that one slice that we were just looking at is going to be equal to, and it's important for me to point out that we're going to be talking about two different volumes here. The volume of one of these slices is what I'm talking about right now. And so we're going to look at it as the volume of a cylinder which is sitting on its side as opposed to it sitting on its top or bottom. So that, of course, is pi r squared h. And for this particular example, we have a radius, which is the height of the function. So that's equal to the square root of 16 minus the midpoint squared. And that came from the y equals 16 minus x squared. Now we have to square it because it's the radius squared, and now multiply it times the height. And the height, of course, is, I'm sorry, not times the height, times the width, which of course is delta x. And delta x depends on how many subintervals. Okay, well then what happens is we take all of those slices and we add them together over the interval that we're talking about, which is from -4 to 4. So let's look at what that would look like in terms of the volume, because this was just the volume of a slice. So the volume total would be equal to pi times 16 minus x squared, which, because I had the square root squared, the squared eliminated the square root, and that's on the interval -4 to 4. And so looking over here now, what I want to point out is, as you increase the number of slices from 10 to 25 to 50, then the approximation for 10, the approximation for 25 gets a little bit better, and then notice for 50 it's even a little bit better. And as the number of slices increases, the approximation gets better and better. And that's something we'll return to later on, where when we increase the number of slices, the number of subintervals, how the approximation gets more accurate. Well, now it's time for you to try a problem. And the problem I have for you is this. Volume of a nose cone. The nose cone of a rocket is a paraboloid obtained by revolving y equals the square root of x from 0 to 5 inclusive about the x-axis. Estimate the volume V of the nose cone by partitioning the interval 0 to 5 into 5 subintervals of equal length. Slicing the cone with planes that are perpendicular to the x-axis at subintervals left endpoints. Constructing cylinders of height 1 based on cross-sections at these points. And then finding the volumes of these cylinders and obviously adding them together to get the total volume of the cone. Here's a diagram that will help you to find the approximation. This blue line is your curve y equals the square root of x, which is being revolved around the x-axis to create the nose cone. Here are the 4 cylinders that you're going to use to approximate this volume. Remember that we are going from 0 up to 5. However, what's happening is we're only using the left-hand endpoint of the cylinders. Each cylinder is 1 unit wide. So with that information, you should be able to now work out the approximation for the volume of this nose cone. So pause the video while you work on this problem, and when you're finished, restart the video to check your solution. Welcome back. Now, let's approximate this volume. This is the way I left it with you. Here's our 4 cylinders, and what you need to know, let me clean this up first. What you need to know is the volume for each cylinder. Well, the volume for each cylinder is V equals pi r squared times h. H in this particular case we said was going to be a fixed unit of 1. So really the volume is just pi r squared. And r in this case, the radius, is going to be equal to the square root of x, because that's what the function is. So our volume is pi square root of x squared, which means the volume is pi times x. For this particular example, we had 4 subintervals, and so the volume would be pi times 0 is that first one. Then you have plus 1, plus 2, plus 3, 4, and we end there. And so this is equal to 10 pi. And if you worked out pi and approximated it to be 3.14, of course, you would say that the volume was 31.41 approximately cubic feet. Another use for the RAM method is in approximating the area under a curve given a graph and some numerical data. Let's try an example. It's called cardiac output. The following table that's on the next slide gives the dye concentrations for cardiac output determination. The amount of dye injected in this patient was 5 milligrams. Use rectangles to approximate the area under the dye concentration curve and then go on to estimate the patient's cardiac output. So I'm going to show you the table, which gives us the seconds after the injection, and then what the concentration of dye was measured to be at that particular time. Now, keeping on this, I'm going to show you what that graph looks like. So here we have the graph of those dye concentrations. Once again, we're approximating this with the area under the curve. So we are going to take the midpoints, and let me use a different color. We're going to take the midpoints and create rectangles just like this. So it's the same process. We were given not a function, though. There's no equation here. But what we were given was the specific information. So for instance, let me take this first rectangle. This first rectangle, like all the other ones, has a width of 2. The height, we're going to have to estimate by looking at the graph. And so this has a height of approximately 1/4. Let me write that a little bit bigger. Height is 1/4. And we would have to do that for each of these other midpoints. Let me take one more, for instance. Let's take the midpoint here and draw my rectangle, which would come all the way down, and then all the way down. And then we have to look across to here, and it looks to be at about, I didn't go quite straight, but about 3 1/4. So therefore, this area would be equal to 2 times each of the midpoints. And I said that the first one was 1/4, and then I didn't do a whole bunch, but then I did one more for you that we said was 3.25, etc., until we get to the end. And in so doing, when you add all those up and then multiply them, you would actually find that the area underneath there is equal to, actually I'm going to put it up here, 45. So there's yet another way that you can use that area under the curve and use the RAM method to approximate it. Now, in terms of the cardiac output, which was the second part of that, what we would have to say is the cardiac output is equal to the original amount of dye, which was 5, divided by this area, which was 45. So let me do that. 5 divided by 45, and then times 60, because we wanted it in liters per minute. And so that when we multiply all that out, we will get 6.7 liters per minute. And that would be the cardiac output of that particular patient. All right, that was a great lesson. And in today's lesson, we learned the rectangular approximation method for finding both the area under curves, the area under a curve that we had the data for, as well as volumes. So be sure to work the exercises that your teacher assigns, and we'll see you next time.